Hi again. A little more talk with forces in motion for the last day. And yesterday we looked at our chart that we had already had at school. And we also looked at some nonfiction text features. After reading our book, Motion, Push and Pull Fast and Slow, we went back and we added some words that I heard about: inertia and acceleration. I also added, based on your comments, things for adding for different ways to move: crawling, rolling, and kicking. And we added a couple more nonfiction text features to our chart: types of print, which are italicized print, bold words, and highlighted words. And we also added captions, important with photographs, because it tells us why the author included that picture and so that we know what that picture is about. Today I'm going to read our last book, our last read aloud for Forces in Motion, A Crash Course in Forces in Motion. A fun story graphic novel. Table of contents. Section 1, Forces that Move Us. What a perfect day, even though everything feels turned upside down. Spinning, flying, jumping, and falling are just some of the amazing ways to move. But there's a lot of science behind the zoom around us. In fact, the world is full of all kinds of motion. Everything that moves needs a force to get it moving. Back for another jump already? You bet. A force is any push or pull on an object. Bungee jumping depends on a force called gravity. It pulls objects toward each other and it keeps us on the earth. Gravity is the reason I fall down, not up or sideways. Phew! Moving can be thrilling, but I need a break. Snap, snap. Hi, Rosita. What are you doing here? Hello, Max. I'm taking notes for the physics class I teach. Why are you just sitting there? Is something wrong? Well, once I sit, sometimes it's hard to get moving again, but once I get going, I often can't stop. That's inertia for you. An object at rest tends to stay at rest. An object in motion stays in motion. That's Newton's first law of motion. A still object needs a force to get it moving. Likewise, a moving object needs a force to change its direction, slow it down, or make it stop. For instance, inertia keeps that stroller rolling. Whee! Until another force comes along to stop it. Ah! To cure your inertia, you just need a little push. Come on, let's go ride the roller coaster. Let's move. Isaac Newton, 1643 to 1727, was the first person to realize that certain laws of nature explained all motion on Earth and in space. He also was the first to explain the idea of gravity. Here we go. I feel like I'm being pushed to the back of my seat. That's inertia. When the ride starts, your body is at rest. When the car moves forward, your body wants to stay at rest, but the chair moves into you. The chair's forward motion makes you feel like you're being pushed to the back of your seat. Wow, how does that roller coaster go so fast? The force of gravity is increasing our speed and acceleration. Speed is how fast we are going at any given moment. Acceleration is how much speed we pick up as we go down the hill. Acceleration causes us to move more quickly at the bottom of the hill than we did at the top. That bar digging into my stomach must be inertia too. You got it. The ride comes to a stop, but your body wants to keep moving. The lap bar applies a force that keeps you from flying out of the car. So the lap bar stopped us from continuing forward on the roller coaster. What keeps that stone from staying in motion? Plop. Excellent question. You can't see it, but a force called friction stopped the stone. Friction happens when two surfaces rub against each other. On Earth, gravity and friction work together to slow things down and make them stop. Brakes on the roller coaster used friction to slow us down too. Come on, I'll show you how. Each roller coaster car has two brake fins attached to its underside. As the cars approach the station, these fins slide between two sets of brake rails. I see. When the brake rails squeeze against the fins, friction stops the cars. I had a great time, Rosita, but I've got to run. My nephew is having his birthday party over at Skater's Paradise. See you later, Max. Section 2. Motion is a weighty issue. Juggling these bowling balls is wearing me out. Ha 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 ha. I didn't know why that guy is so tired. Juggling is easy. The juggler on the right is tired because he is using more force to throw and catch heavier objects. He's showing us Newton's second law. The amount of acceleration that a force can produce depends on the mass of the object. What's a mass, Uncle Max? Mass is the amount of matter in an object. The bowling ball has more matter in it than the tennis ball, so it feels heavier. Think about it. Which ball would be easier to juggle, Nick? Gravitational pull. Weight is different from mass. Weight is determined by gravity's pull on an object. Each planet in our solar system has a different gravitational pull. If you traveled to each of the places below, your mass would always be the same, but your weight would be different. Multiply your weight by the number shown below each planet to find out how much you would weigh there. If you weigh 100 pounds on Earth, you would weigh 38 pounds on Mars and 236 pounds on Jupiter. I have another way to think about Newton's second law. I need 2 volunteers. Pick me! I'll do it. I'm going to push both of them with the same amount of force on a level surface. Who do you think will accelerate faster? Johnny's bigger. He'll go faster. Jenny's an awesome skater. She'll win. Both of my arms are equally strong, so the amount of force will be the same. Let's see who gets a faster start. Like the tennis ball, Jenny has less mass than Johnny, so she gets a faster start with the same push. Johnny would need a stronger force to get moving as quickly. I'm like the tennis ball. Does that make me a bowling ball? Uncle Max, Jenny won the race on a flat surface, but I've noticed that the bigger kids always travel farther down than the smaller kids when skating down a ramp. Sometimes having more mass can give you an advantage. Let's have Johnny and Jenny race again. In the last race, we wanted to see who would get a faster start. This race is for distance. I'm going to release you at the same time. We'll see who travels further without pumping. Johnny's got it in the bag. No way, Jenny will beat him easily. Do you see that? Gravity pulls them down the ramp, but Johnny travels farther than Jenny. Max, what happened? I got a good start, but Johnny just passed right by me. Johnny's larger mass takes more force to slow down or stop than your smaller mass. Friction between your wheels and the ground was the main force slowing both of you down. Johnny needed more friction to stop, so he traveled farther. Time for cake! I don't think these kids will let a little friction stand between them and chocolate cake. Section 3, Give and Take. Making balloons zip around is one of their favorite pastimes. You like playing with spaceships, do you? Spaceships? These are balloons. Just like air coming out of a balloon pushes it forward, hot gases thrust a rocket into space. In fact, these balloons are perfect illustrations of Newton's third law. What do you mean? For every action, there is an equal and opposite reaction. Let's go for a swim, and I'll show you what I mean. Octopus jets. An octopus uses Newton's third law to swim. It squirts jets of water out of a tube in its body to push itself through the water. Newton's third law tells us that every action involves a pair of forces. An action's force creates a reaction of equal force in the opposite direction. My jump is the action. The reaction is the raft moving backward. Look at that raft go. Newton's third law is easy to see when you start looking for it. That's right. For example, as we swim, we pull our arms through the water. This motion causes the water to push back while we move forward. All this talk about action and reaction has me ready to try some more rides. Do you two want to join me? Yeah, all right. Section 4, Round and round we go. You guys are making me dizzy by running around in circles. I know a ride you'll love. Look at the swing ride. What would happen if those swings suddenly flew off the center pole? I bet it would keep going in a circle for a while and then fall. Nice try, but no. A force is needed to keep objects turning. The inward force that keeps those chairs moving in circles is called the centripetal force. But if the chain on a chair breaks, centripetal force no longer acts on the chair. The chair would fly off in a straight line. Whoa! Looks like it's our turn to ride. Are you sure this ride is safe? Perfectly. Whee! That ride was awesome. Is centripetal force used for anything besides rides? Yes. Gravity is the centripetal force that keeps astronauts and their spacecraft in orbit around the Earth. Really? I wish I could go to space. We may not be able to go to space, but we can feel what it's like. Follow me. This ride is crazy, Uncle Max. Just watch the penny I'm holding when we drop. Whoa, the penny looks like it's just floating there. It's magic. Actually, it's science. When we're in free fall, and so is the penny, we're all falling at the same speed, so the penny looks as weightless as we feel. Do astronauts feel weightless in space because they are falling? Yes, orbit is a free fall in a circle. Gee, Uncle Max, is everything in this park a science lesson to you? Of course. Just look at how much there is to learn. Bumper cars are a fun way to experience action and reaction. The merry-go-round uses centripetal force to keep riders moving in circles. And roller coasters teach us about inertia, speed, and acceleration. Bungee jumping looks like fun. You wouldn't be crazy enough to do that, would you, Uncle Max? Oh, I don't know. What do you say? We give it a try. Forces in motion are all around you. Enjoy the ride. There's our glossary. There's our internet sites and more books to read. And there's our index. So as we wrap up forces in motion, Are you able to tell me what forces are? How do forces help us? What's gravity? Why is gravity important? And what about friction? What does friction do? How does friction help us? Can you give me an example of friction? If you can answer any of those questions, go ahead and message me on Class Dojo.